Hi everybody, this is Mr. Martin again, talking to you about transformations. On my last video, I talked to you about translations and rotations. This time I'm going to talk to you about reflections and dilations. And yes, I had these two flipped up on the introduction last time. Sorry about that. I'll try to get better. Here's this video. Like I said, we'll do reflections and dilations, and I promise you this is actually true. Reflections. You see a couple of reflections down here in terms of mathematical reflections, and you see the picture reflections also that kind of provide us real-life examples. So a mathematical reflection is exactly what we have in mind with that it preserves the angle and distance, like we said, so we should have a congruent image. That is a rigid transformation. The orientation flips in the figure, and you see that right here. The orientation, this one had the straight edge on the bottom. In terms of the long edge, they're all really straight, but long edge is now on the top in this one. And then on this image here, the direction of the line seems to have flipped itself in terms of how it fits. For the swan, same thing. The orientation of the swan seems to change. Its neck is now kind of going the opposite way that we thought. The line of reflection mathematically is equidistant from the original and the image. And so what that means is that the pink segment here is exactly equal to the pink segment on the other side. The distance from the mirror line, or the line of reflection, up to this point on the original image is exactly equal to the distance from the mirror line to this point on the original. Okay? And the line of reflection, since each part of that line of reflection is equidistant to these points on the figure, that line of reflection is the perpendicular bisector of the various parts of the segment. So if we called that point A prime and this point A, the original point A prime on the image, then the mirror line, or the line of reflection, is the perpendicular bisector of the segment from the image point to the original point. And that's true also for this point and for any point that I could imagine along each segment here. So let me give you a little bit more of a picture of what that would look like. And so I have a line of reflection here that is line EF. I have my original figure that is ABCD, some quadrilateral that I created, and I have the image A prime, B prime, C prime, D prime. Notice that I had to go in a counterclockwise order here, whereas I went in a clockwise order for my points on the original. And I have a few things hidden. We show all the hidden objects here, and I've got the line A prime, or line segment A prime drawn, as well as B prime, D prime, and C prime. And if I create the midpoints of each of these, those ought to be on line EF. And so I'm constructing those midpoints. And then, if I take any one of those midpoints and ask for a perpendicular line to that segment, it ought to be line EF, and we find indeed that it is, and I can test that over here as well. And it doesn't create any new line, it just shows me, hey, wait, you already have that. So line EF is the perpendicular bisector of each of these dotted segments. Well, how can I use that? It's kind of useful information, but how can I use that? If I go over here and I have a figure that I want to reflect, so I mark it mirror, and I want to reflect this figure, then what I know is that if I go on a perpendicular line from EF that goes through A, or through D, or through B, or through C, then whatever that distance is, it will be equidistant to the other side on the image. And that I can use in order to create my image for a reflection. So what I might do is I might say, okay, I want B, and I want line EF, and I want the perpendicular line there. And then I want to specifically know that intersection. And now that I know that intersection, I can measure this distance and copy that same distance there. I can create a circle by center point, and so the radius here would be equal to the radius there, and the intersection, that point right here, is my B prime. And I could repeat that process for each of these others in order to construct my image. I'm going to go ahead and pause the video momentarily so that I can construct this much more quickly for you, and then we'll be back and I'll show you that indeed ABCD has been reflected through that process. See you in a moment. Okay, I'm back. I've created all the circles, all the perpendicular lines, and even connected my intersection points. And so I believe that the figure right here is the reflection of ABCD. It seems to look like it, but let's indeed check to verify. So I'm going to just grab these segments because it's a little bit faster than trying to grab the points, and I'm going to transform and reflect it, and indeed it lands exactly on that image that I had. There is no other image, and so those points would be labeled A prime, B prime, C prime, and D prime. And I'm going to go back over here to this little bit cleaner figure, and you'll notice that as I move this figure around, those points that are on that perpendicular bisector line EF also move around, just in order to make that image fit in terms of what we want. And the image itself rotates around to make itself the image. And we can do that even within the figure. We can have our reflection line be within the figure or outside of it, either way. So that's reflections, and the perpendicular bisector understanding is something I do want you to remember. We'll go back now and we get to talk about the next portion, which is a dilation. A dilation is the transformation that is not rigid in terms of the main types of transformations. That tells us that neither angle, well, it tells us that angle and distance as a whole are not both preserved. It turns out that angle is preserved, distance is distorted. Mathematically, that makes the figure that we're looking at similar to, but not congruent to, the original. So in this image here, A prime, B prime, C prime is similar to ABC because the angles are congruent to the angles in ABC, but the side lengths are not congruent. The side lengths have been changed by a scale factor. Scaling it is another synonym for a dilation. We usually talk about scale factors. As you'll be aware, scale factors greater than 1 enlarge the figure and less than 1 reduce the figure. A dilation goes from a specific point, just like a rotation, and that point is called the center of dilation. And in this picture, the center of dilation is point O. And so we've figured that out. The center of dilation there determines a distance to each point. And so OB is a distance, OA is a distance, and OC is a distance. The distance to now the image is adjusted according to that scale factor. And so in this example, the scale factor is 2. Get my little dialog boxes out of the way. Meaning that the distance OB multiplied by 2 becomes the distance OB prime. The distance from OA multiplied by 2 becomes the distance OA prime. If the scale factor were something other than 2, then that scale factor is what would show up here. If it were a reduction, then, say by 1/3, it'd be OB times 1/3 would equal OB prime. And OA times 1/3 would equal OA prime. And so that's kind of the idea there. And so then we get back to our sketchpad image, and this is my figure, quadrilateral ABCD again. And point O is going to be my center of dilation. And so if I want to dilate that, I will choose dilation, and now I get to play with my ratio. Here this would be a dilation by 1/2. I could do a dilation by 5/2, and now that because that's larger than 1, the figure gets larger. I could do a dilation by 2/2, and I get the exact same image, which should be predicted because the scale factor is exactly the same. I could do whatever I choose to do. I'm going to go ahead and go with let's do 1/3 and dilate that, and I get a little bit smaller of an image. And notice as I move that around, these types of things change. But if I were to construct the line segment OA, then you'll notice that A prime is on that line segment. And if I construct my other line segments from O to the original, you'll notice that OB has B prime on it, and you'll notice that OC has C prime on it, and you'll trust the same will be true for D prime. If I go and measure the distance from O to B prime, that should be exactly 1/3 of the distance from O to B. And so let's check and find out. And it looks like it might be kind of close. Well, let's go ahead and take that and calculate this measurement, BO, and notice that it was rounded up here, so that might account for things. Times 1/3 times 1/3. Oops, nope, I want BO prime to be multiplied by 3, not by 1/3. And that should be exactly equal to OB prime, no matter how I move things around. And indeed, it does seem to be true that those are exactly equal. All right, I hope this has been informative to you, and I look forward to seeing you on a future video. Thank you.